So this is the second section of the central limit theorem, second and final section, and we're going to be applying the central limit theorem to other distributions. Now it doesn't matter what distribution you have, the sample mean is always normally distributed. So if it's a Poisson distribution, geometric distribution, negative binomial or binomial, it's always normally distributed. But what we want from our distribution is we need to know what's the mean and the variance of a population. So we start with a Poisson distribution. So we'll just remind ourselves. So if we've got a Poisson distribution where things happen at a rate of lambda, then the mean of that is going to be lambda, and the variance is also going to be lambda. Okay, so we can use that when we solve problems. Next, let's look at the binomial distribution. Now with the binomial distribution, remember our two parameters are n and p, and remember that the mean is n times p, and the variance is going to be np times 1 minus p. What next? Geometric. So if I have a geometric distribution, so that's where things are distributed like this, where we have p there, then the mean of a geometric distribution is 1 over p, and the variance is 1 minus p over p squared. I'm pretty sure a lot of this stuff is in the formula book, but it's good to have it in one place. And then the next one we have is the negative binomial. So the negative binomial distribution, which we can write like this. So we could just write NB here, and our parameters are R and P, and the mean of this is R over P, and the variance of this is R times 1 minus P over P squared. And for all of these, if n is sufficiently large, then for all of these distributions, the sample mean will be normally distributed like this. And we're going to use the various means and variances that we get from each one of these distributions, and then we can put them in here. And remembering that, and I almost forgot here, that the variance here is the variance that we get from our distribution over n, which I almost forgot, and that's our sample size. And just like before, we're looking really, ideally we want n to be greater than 50 for it to be like a good model for the sample mean. Okay, so what we've got here is a supermarket manager trying to model the number of customers that visits her store each day. She observes that on average 20 new customers enter the store every minute. Now if you see information like that, we need to be thinking about what type of distribution is this. So we've got things happening at an average rate over a fixed time period. So we should be thinking, right, this is a Poisson distribution. Okay, so part A, because remember in the exam it doesn't tell you what distribution it's going to be. Part A, calculate the probability that fewer than 15 customers arrive in a given minute. So the first thing we must do is to set up our random variable. So basically this is the number of customers that enter the store every minute. The number of customers entering or arriving at the store, entering the store every minute or in a minute. So we set that up first. So we know that this random variable x, the number of customers entering the store, is a Poisson distribution, and the rate that they arrive every minute is 20, and we want to find the probability that it's fewer than 15. Like that, so it's less than 15, doesn't include 15. Now we need to change that to less than or equal to 14 because it's a discrete distribution. Make sure you're on Poisson CD on your calculator. So I get this decimal 0.104864 like this. So I'm going to round it to 4 decimal places. So 0.1049 for DP. Part B. Find a probability that in 1 hour, so our time scale has changed, so we need to set up a new random variable, no more than 1,150 customers arrive. So let's set up Y since it's the next letter in the alphabet, and this will be the number of customers entering the store in an hour. The number of customers entering the store in 1 hour. So it's not a minute anymore. So Y is going to be the random variable where the rate at which it happens in an hour, so we need to scale this up, so it's going to be 20 times 60, since there's 60 minutes in an hour. So this is going to be a Poisson with a mean of 1,200, and we want to find a probability that no more than 1,150. So this is going to be less than or equal to. So just notice the difference in the wording. This one was fewer than 15, and this is no more than. Yeah, so that makes a difference to our inequality symbol that we write down. So let's type this in. So we will have, just need to go on the right thing here, Poisson CD, yeah, that's right. So Y is going to be 1150, my mean is 1200, equals, and I get 0.075, and it's 7728, it carries on, rounding it to 4dp, 0.075, and that rounds up to 8. So also this is 4dp. Part C, use the central limit theorem. Okay, so the central limit theorem will say basically that all of my samples are normally distributed to estimate the probability that in 1 hour, no more than 1,150 customers arrive, and then we're going to compare our answer to part B. Do we get a similar answer or a slightly different answer? Now there are two ways we can do this question. We can either use the random variable x and look at the number of customers entering the store in a minute, or we can use the random variable y and look at the number of customers entering in an hour. Either way, the mean amount of our samples is going to be normally distributed. Yeah, so that's going to be the same for both. Now, whichever way we do it, we should get the same answer. So let's start with using x as the random variable. So here we know that customers enter at a rate of 20 per minute. Now, if it's over an hour, that means basically we're taking 60 samples here, and the standard deviation is going to be 20 as well, because remember, with a Poisson distribution, the mean, or the rate equals the mean equals the standard deviation. Okay. Now, if we're going to be using this time scale as of a minute, then when we work out the probability that no more than 1,150, we need to scale it down, because 1,150 in an hour divided by 60 basically tells you how many in a minute. So that would be 1150 divided by 60. So we're talking about 19.1666666 recurring. Okay, so actually what we're going to be working out is the probability that it's less than or equal to, and this is 115/6. So we go to our normal distribution on our calculators. So menu 7, normal CD. Now I'll type in, maybe I'll draw a little diagram so we can see what we're working out here. Yeah, so here my mean is 20. And what number was it? 115/6. Where would that number go? I can't remember what I said it was. Let's go back. 115/6. What's that? 19.16. Okay, so it's over here. Like that. 115/6 on 19 point whatever it was, 6. And it's no more than that, so I want to work out this area. Less than that, so that's basically what area I'm working out. So we'll go to normal CD, back to normal CD. So I'm going to type in a lower limit. It needs to be more than 5 standard deviations away from the mean. So more than the square root of 20/60 away from the mean. So I'll stick 0 as a lower limit. Upper limit is going to be this 115 divided by 6. The standard deviation, well, that's going to be the square root of 20/60. And the mean is going to be 20. And if I do that, I get an answer of 0.074457. So to 4 dp, I will get 0.0745, 0.0745. Okay, so I'm just going to keep that there. So this is one way to do it. Another way to do it is to say, right, let's use the random variable y, which is the number of customers arriving in a minute. Now, if we do that, it's still going to be normally distributed. Sorry, not in a minute, in an hour. In an hour, we have this many customers arriving. Okay, the variance is still that. But how many samples are we taking? Just one over the course of the hour. So you could say, right, we're taking one sample of 1,200 customers. And then we're going to work out the probability that the mean of y. Now we can just use 1,150. Okay, so we don't need to scale it down because basically we're using the fact that it's an hour. So here I'm going to use a lower limit of 0, upper limit of 1150, a standard deviation which is the square root of 1,200 and a mean of 1,200, and I get exactly the same answer. So this is a different way of doing it. I get 0.074457. Yeah, I get exactly the same answer. It will still round to 0.0745. So I could do it either way. Now the question says what we need to do is to compare our answer to part B. Now part B, what did we get an answer of? It's over here, look. There it is. Not big difference. Okay, so it's quite close. So I would say that the central limit theorem gives us a good approximation. So I could say answers close. Answers are close. So the central limit theorem, I'll just put CLT, gives a good approximation, yeah, for that one. Billy is the captain of a football team. Each week he gets a team together by calling his friends one by one and asking if they would like to play. The probability of each friend agreeing to play is 2/3. Once he has 10 other players, he stops calling. So what happens with this type of distribution? How are we going to decide which type it is? Well, there's more than one success. If there was just one success and we stopped, or it was just one success and we worked out the probability, that would be geometric. Because we've got multiple successes and we stop, or we want to work out the probability of getting those multiple successes, this is the negative binomial. So negative binomial. So we need to be thinking about that in this question. Again, it won't tell you in the exam that you use that you need to use a negative binomial. And it says calculate the number of friends Billy expects to have to call to find 10 other players. So the first thing we do is say our random variable, we use x in this case. What does x stands for? Well, it's going to be the number of friends Billy expects to call. So the number of friends Billy expects to call. Okay. So whenever we set a random variable, it's normally the number of something, isn't it? Then we say, right, this x is a negative binomial, so just put negative binomial NB. Now, whenever we have a negative binomial, we need two things. We need R and P. Now, R is going to be the number of trials or the number of successes at which point we stop. So when I've got 10 successes, I stop, so R is 10. And what's the probability of success? Well, it's 2/3. So the parameters for the negative binomial are R and P. Now when it says expects to call, there's almost a clue in the word, isn't there? Expect, the expected value is E of x. So we actually now need to calculate E of x. That's the mean of this negative binomial distribution. And E of x is R over P. R in this case is 10. P is 2/3. So if we do 10 divided by 2/3, we get 15. Okay, so that's E of x. Part B says find the probability that Billy has to call exactly 12 friends. So we want to find this, the probability that he has to call exactly 12 friends. Now we've got a formula for this, and I'll write the formula down. Let me write it in red. And the formula for this is, if I want to find the probability of x equals x, it is equal to NCR. Now I'm going to write it column like this, the NCR, because it's too fiddly to write it next to the C. So that times the probability of success times by, or to the power of R, and then 1 minus P to the probability x minus R. So this is in the formula book, so we can just plug our numbers in. And in this case, where we have x equals to 12, just write that down, x equals to 12, and R is equal to 10, and P is equal to 2/3. So everything just gets plugged into the formula. So we are going to have 12 minus 1, 11. So you've got basically like 11 C9, because it's 10 minus 1, times by 2/3 to the power of r, which is 10, times by 1 minus p is going to be 1/3 to the power of x minus r, so that's going to be 12 minus 10, which is 2. So we'll put this on our calculator, and we get 0.105976. So again, 4dp, 0.10, and that becomes 60. Okay, to 4dp. Part C. Just before part C, it says, in a season, Billy's team plays 25 matches. Estimate the probability that the mean number of calls per match Billy has to make was less than 15.5. So basically it's like the 25 samples, yeah, of this number of calls. So we already have the mean, so we're going to model this by the central limit theorem. So we can say by the central limit theorem, we're going to be able to model the mean of these with a normal distribution. Got my lines the wrong way around. That's a bar, that's a squiggle. And we need to know what the mean and the variance are. Now the mean we've got already, that was 15. So we also need to work out var x, and var x is going to go in here. Okay, so let's do a different colour. Var x, and I believe this is in the formula book, is r times 1 minus p over p squared. So let's put the numbers in. So r was 10 times by 1 minus p, so that's going to be 1/3 divided by 2/3 squared. So let's work that out. And that gives us 15 over 2, which is 7.5. So now we know our variance is 7.5. And the sample, well, that's 25. And what we want to do with this is we want to find the probability that this sample mean is less than 15.5. So the rest can just be done on the calculator now. So we change mode and we go back to where we can type in our normal distribution, normal CD. We type in a lower limit, something small, so we'll do 0, an upper limit of 15.5. Our standard deviation is going to be the square root of 7.5 divided by 25, so we can just type that in. And our mean is going to be 15. And then we get 0.819344, and it goes on. Again, round to 4 decimal places, 0.8193. So there's our answer to part C. So let me just highlight them. So part A we worked out E of x, didn't we? Part B we worked out the probability that he has to call 12 friends. And in part C we worked out the probability that the mean number of calls in 25 matches would be less than 15.5. Okay, you should now be able to do exercise 5b on pages 81 to 82. So just as a quick recap, whatever the distribution, we have the sample mean. So let's write this in proper English. For any distribution, or any distribution, the sample mean can be modelled by a normal distribution so that means we will have something like this, okay, where the mean of this is going to be the mean of the population. Now that might be mu or e of x, and the variance of this, so the variance of our sample mean is going to be the original variance over the square root of n. Actually, let's write variance. I've been saying variance and then I'm writing down standard deviation. So that's squared, that's n. Now this at the top could be var x as well. Yeah. So look out for the types of distribution, looking for key phrases. Is it a Poisson distribution? Is it a geometric? Is it a negative binomial? And then pick the one out that you need and then use that to find your mean and your variance. Then we can do the modelling. So actually we could have lambda here as well, couldn't we? And this also could be lambda for the variance depending on the distribution.